These are the video notes for Objective 9, Trigonometric Form of Complex Numbers. We want to start this lesson with what a complex number is. So a complex number can be written in the form of a plus bi, where a would be considered the real part of a complex number, and b is considered the imaginary part of the complex number. And what makes a number complex is the introduction of the imaginary part. Keep in mind, because of this format, that all real numbers are by default complex numbers. They just have an imaginary part of 0. So with this, we can introduce something called the complex plane. And on the complex plane, we define the x-axis as the real axis and the imaginary, or the y-axis, as the imaginary axis. And because of this definition of the complex plane, we can graph any complex number as an ordered pair a, comma, b. And the same rules that apply toward the Cartesian plane apply. Same rules that apply for the Cartesian plane with the negative axis, the positive axis, the negative axis, and the positive axis apply when graphing complex numbers. So let's graph the complex number just for a quick example. 2 minus 4i. In this complex number, we can think of it as an ordered pair 2, comma, -4, with 2 being the real part and -4 being the complex part. So if we were to graph this on our complex plane, we would go 2 on the real axis and -4 on the complex axis. This sort of graphing is what's going to allow us to convert a standard form complex number into its trigonometric form. Once we've established this, and I'm going to keep our same example of 2 minus 4i, we can introduce the absolute value of a complex number. So the absolute value, or modulus, of a complex number is written in the following notation. And it's essentially the distance from the origin to the location of the complex number in the complex plane. So it's going to look a lot like the distance formula, or a lot like the Pythagorean theorem if you were solving for the hypotenuse. So this is the absolute value, or modulus, of a complex number. Knowing that, what is the absolute value of 2 minus 4i? And so we'll write the square root of 2 squared plus -4 squared, which evaluates to the square root of 20, or simplifies to be 2 radical 5. Now this value, when we're writing complex numbers in trigonometric form, is the r value. And if you take a look at our graph, which we still have, and imagine connecting it to the origin, since we know that this absolute value is the distance from the origin of the complex plane to the complex number, you can see that it forms a right triangle, and that the 2 radical 5 is the hypotenuse. Well, this directly leads us to how to write a complex number in trigonometric form. So the next step, now that we know the hypotenuse, or the absolute value of the complex number, is that we can actually figure out the trigonometric equivalent of 2 minus 4i in the complex plane. So the key to doing that is to find the angle that your complex number forms at the origin. And since I was given the side length of 2 and the side length of -4, you can say that I was given the opposite over adjacent ratio, which we learned in an earlier objective was tangent. So tan alpha equals -4 over 2, or using our inverse function, alpha is equal to the inverse tangent of -2. Go ahead and type this into your calculator for an angle measured in degrees. And you get that alpha is equal to -63 degrees. However, when we're writing our complex number in trigonometric form, we want to use the smallest possible positive angle. So if alpha is negative 63 degrees, but it's located in quadrant 4, we're going to go ahead and add 360 degrees to our result. And we find that theta, or the full angle, terminal angle, is 297 degrees. Well, now we have both pieces. We know that r is equal to 2 radical 5, and we know that theta is equal to 297 degrees. Let's put this all together and take a look at the trigonometric form of a complex number, which is what our learning target is focused on. With these two pieces of information, we can say that the complex number 2 minus 4i is equal to 2 radical 5 cosine of 297 degrees plus I sine of 297 degrees. And the formula for the complex form of the trigonometric form of a complex number is z equals r cosine theta plus I sine theta, where this is our absolute value and this is our least positive angle. For the rest of the video notes, we want to practice converting between complex form to trigonometric form and from trigonometric form to complex form. So we've already seen one getting from complex into trig. Let's take an example where we take trigonometric form and rewrite it in complex form. Let's take a look at square root of 2 cosine of pi 6 plus I sine of pi 6. We're going to go ahead and write this trig form into the standard form of a complex number. In order to do this is generally a little bit more straightforward because all we have to do is simplify this expression. So we'll start by figuring out what the cosine of pi 6 is. And since pi 6 is in the first quadrant, the cosine is rad 3 over 2. Plus I, and we're going to let sine of pi 6 become the coefficient. So the sine of pi 6 is 1/2. And then we distribute our r. So our answer for the complex form of this complex number is rad 6 over 2 plus rad 2 over 2i. We're not going to combine these into a single fraction because if you remember, the complex form is a plus bi, and by leaving it like this, I can see that the real part is rad 6 over 2 and that the imaginary part is rad 2 over 2. This concludes part 1 of the video notes for Objective 9, Trigonometric Form of Complex Number. In this section, remember, we just focused on how to get from trig form to complex form, and in the beginning, from complex form into trig form.